So, good morning. Yesterday we had a brief introduction about the classification of the different regimes like the macro scale, micro scale and nano scale based on the Knudsen number. The non-dimensional Knudsen number was introduced to be the single most important non-dimensional number that governs the basically the effect of assuming a continuum approximation typically in the small Knudsen number values, and if you are increasing the Knudsen numbers to larger and larger values, this approximation fails, and finally we are going to the free molecular limit at Knudsen numbers going to infinity, where none of the continuum approximations work, and therefore we have to use what we call as Boltzmann transport equation model based hypothesis. So, therefore, for solving the problems at large Knudsen numbers, we have to be a little bit careful where the approximation based on continuum hypothesis can be used, and I want to therefore once again summarize the different regimes where the continuum hypothesis can be valid. So, if you look at Knudsen number values much smaller than say 0.001. So, this is a thumb rule, but need not be exactly 0.001, sometimes people take it as 0.01, but generally the thumb rule is that for the limiting case of Knudsen number going to 0, this is where the actual continuum approximations are valid, and this is called the macro scale regime, right. And so, when you say continuum approximations are valid, you definitely use the assumption that there is a local thermodynamic equilibrium, if not globally, even at least locally it should be satisfied. That is why this is a continuum approximation, and at the boundaries of the between the system and the fluid. So, you do not have any slip in either the momentum or in the temperature. Okay. So, this is what you have been we have been generally dealing with in the classical thermodynamics or classical heat transfer and so on and so forth, classical fluid mechanics. So, now we can also have systems where the so called mean free path or the length scale, mean free path could be quite large compared to the length scale, or the length scale could be quite small compared to the mean free path. So, this could put the Knudsen number in a range between 0.01 or 0.01 to somewhere up to a maximum value of 0.1. Okay. So, this case there is a possibility of using the continuum equations that were still used in the macro scale regime, but with the fact that you have to account for the slip between the fluid and the system boundaries. So, slip here happens not only for the momentum, but also for the energy equation. The temperature also shows a slip, characteristic slip. So, therefore, we have to account for the boundary conditions through the accommodation of slip at the boundaries through slip boundary conditions for both velocity and temperature, and therefore, this regime is called slip flow regime. This is particularly more suited for the gases. Okay. So, gases are shown to have pronounced slip at the boundaries compared to the liquids, and therefore, the kind of regime that we are talking about is more suited for gases. Now, for the liquids, since the mean free path is smaller, you may rarely find liquids in the micro scale at least, which are tending towards a Knudsen number of 0.1 or greater than that. So, usually gases can approach this quite easily, but not so easily with liquids. And then we were talking about what is called transition flow yesterday in the map that I showed you. So, if your Knudsen numbers are greater than 0.1 and less than 10, okay. So, definitely there is no question that there is a slip happening at the wall, and apart from that there is also question of the validity of using continuum model outside. So this is a problem where people have been trying to use different formulations, alternate formulations for the Navier-Stokes equations. So some people refer to this to the extended Navier-Stokes equations. So although people have been trying the higher order formulation of Navier-Stokes equation here, but strictly speaking, you cannot use the continuum models at all, and even the extensions of continuum models may not give you satisfactory results. And finally, the case where your Knudsen number is greater than 10, that is the high Knudsen number case. With respect to gases, they are rarefied, highly rarefied flows, and they are referred to as the free molecular flow. And people analyze this by what in the rarefied gas dynamics they refer to as kinetic gases. Okay. So the Boltzmann transport equation is used in the kinetic theory of gases, and that can be also used for other energy carriers as well, need not be gas molecules, but the phonons which we will introduce, and then you have electrons. So the same Boltzmann transport equation which supposed to be for used for the rarefied gas flows in the free molecular limit can also be used in other media as well. So generally this is the these are the different regimes, and these are different governing equations and boundary conditions preferred for those particular regimes. Okay. So then we just also list down what are the distinguishing factors typically in the extreme high Knudsen number limits. So one is that you have what we call as dimensional effects. Okay, this is very particular at nanoscales. For example, if you look at the bulk properties, they are all independent irrespective of whatever dimensions you take. For example, thermal conductivity is a good example. So you measure thermal conductivity and you do not care whether the size is millimeters or centimeters or meters, the value is the same. Whereas if you go into the nanometer dimensions, you find that they exhibit strong size effects. So the thermal conductivity becomes a function of also the length scale. So this is a particular characteristics of high Knudsen number limit. So we will see that why it happens. So why this size effect should happen at nanoscale. And you also have viscous dissipation could be a very important role at small length scales. You have strong heat generation due to viscous dissipation, which becomes very significant. If you do the scaling analysis, you will find that at small length scales of all the terms in the energy equation, the viscous dissipation will become very significant and cannot be neglected. And sometimes even compressibility can be important. Rarefaction is definitely, if you look at gases, these are associated with low pressures. So high Knudsen numbers, so therefore rarefaction will be very important. Okay. So now slip of both velocity and temperature becomes extremely important as well. Okay. We will see that in when we go to microflows, because the slip as such we are still dealing with continuum outside and just changing the boundary condition. So this generally is applied to microflows, not nanoflows. And we also have what we call as thermal creep. Okay. So in this case, so we have a phenomenon called thermophoresis. So thermophoresis is a case where your gas molecules can diffuse from the hot end to the cold end. Okay. So now you can also have a reverse effect called thermal creep, and you can also have other surface forces which are playing a very important role, and this could be used also to drive flows at micro scale. Okay. So we will see some of these effects as and when we go into the particular topic, but you can say that there are number of important factors which come into play at such small length scales, which are not so important relevant at the macro scales. So yesterday we talked about the Moore's law and the problem associated, the bottleneck associated with following the Moore's law over a period of time now. and also the heat dissipation problem happening in microelectronics. So, we also discussed about the 3 levels of cooling and so on. So, if you once again go back to the microelectronics, so we now know this 3 levels of cooling, out of which the level 1 is a problem with the materials, level 2 is something that we can deal with by using the micro technology, like using micro channels and so on. So, if you look at the level 1, so this is typically within the particular chip and within a particular semiconductor device. Okay. So, we are going into now the nanoscale regime. So, why do we have a heat generation or generation of hotspots, what we call as hotspots within the particular semiconductor device that raises this thermal bottleneck problem. Okay. So, typically if you take a silicon on insulator device, so this is the most fundamental semiconductor device. So, where you have a silicon layer which is actually deposited over a buried oxide layer. So, this is something like a silicon dioxide SiO2 over which you have a thin silicon layer. This silicon layer could be as thin or as thick as a few tens of nanometers. Okay. And typically this is your semiconductor device. So, you have current, you have a potential at the gate, you have a source, you have a sink or the drain, and then by controlling the potential between the source and drain, you can basically control the speed with which the electrons move from the source to the drain. You can also control the channel width through which the electrons tunnel through by adjusting the gate potential here. Okay. So, nowadays what is happening is, because of the higher processor speed, you need faster electron transfer from the source to the drain. Okay. So, typically you are applying higher potential differences between the source and drain, and what is happening, the channel sizes are becoming smaller and smaller. The electrons have to move fast, okay, too many of them at the same time. They cannot go through a very big channel because the sizes of these the silicon layers are becoming thinner and thinner. So, therefore, what happens is the substrate, the silicon itself has atoms, and therefore, we can understand that these electrons have to basically propel through this atomic structure, and they usually collide with this lattice structure, and usually this collision will result in the generation of heat, okay, at the fundamental level. So, therefore, it is not just the electrons are moving without resistance, they are facing resistance due to the lattice in the background, and therefore, this collision is bound to generate heat, and what we refer to as usually the source of the generation is around the gate and the drain region. So, this is where the electrons usually tend to get heated up. So, these are hot electrons, typically very high temperatures, and these electron temperatures are typically order of magnitude higher than the base lattice temperature. Okay. So, this results in generation of what we call as hotspots. So, localized hotspots. So, all this is local thermal non-equilibrium. So, everything is non-equilibrium process here, and so this once the hotspots are generated, so number one is prediction of these hotspots. So, if you use the Fourier's equation at these length scales, you will be usually under predicting the hotspot temperature as well as the heat fluxes. Okay. So, they will fail at this particular scale, and again the next aspect is how do we remove these hotspots. Now, these hotspots become also a bottleneck when you have a junction between a metal and a dielectric. Okay. So, these are the interfaces, for example, between a metal line and a dielectric, and usually there is also a thermal interface resistance between the metal and dielectric, leading to this hotspot generation. Okay. Similarly, people have been trying out lot of novel materials where you can improve the thermal conductivity in a certain direction. So, and this can be achieved by using typically what we call as carbon nanotube arrays. So, over the last decade or so, carbon nanotubes have emerged as a very potential materials for microelectronics, because you can tune their electrical and thermal conductivities in certain direction to be enormously high, okay, and they can be grown vertically on substrates like silicon dioxide like this, and you can use them as the thermal interface materials, okay, and thereby you can actually reduce the amount of interfacial thermal resistance and reduce the size of these hotspots and so on. So, there are different techniques to measure the thermal interface resistance. So, we will be talking about this towards the end, where we will briefly go over the experimental methods that are used in micro and nano scale. But what are the key thermal issues therefore? So, one is the effect of small length and time scales on the energy transport. So, you have to understand that part which cannot be predicted with the classical constitutive equations. The hot spots, especially when you are looking at silicon or insulator kind of devices, number one, and semiconductor metal interconnects due to the interfacial thermal resistance. And why do they arise? Because of the non-equilibrium between electrons and the background lattice. So, right now we will introduce this background lattice vibrations particularly with some as a virtual particle called phonons. Okay. So, they are just like photons, as they are virtual, you cannot really find a phonon inside a metal. So, they are just lattice structure and vibrations. So, since we have a wave particle duality, you can always associate this lattice vibrational waves with some particle called phonons, and you can give them some certain energy and so on. So, this interaction between electrons and phonons are going to be at non-equilibrium all the time, and therefore, they result in the generation of these hotspots. So, what is important if you are looking at better thermal management is to understand thermal interface resistance well, generation of these hotspots, and how do we mitigate them by means of efficient materials such as using carbon nanotubes. The other, so we have two aspects. One is the effect of small length scales, which we described by taking an example of a micro or nano electronic device such as a semiconductor device here. The other could be small time scales. So, if you look at lasers, for example, okay, there are applications of laser everywhere, okay, and usually the laser pulse width can range from all the way from milliseconds to what we now use in some applications to femtoseconds, that is 10 power minus 15 seconds. Okay. So, the laser time duration or the pulse width anything less than a few nanoseconds. So, of the order of picoseconds, 10 power minus 12, 10 power minus 15 again indicate that they are extremely fast time scales, okay, compared to what you can actually physically observe. Okay. So, for example, if you are using such kind of lasers to ablate some tissues or metals or whatever, so the actual physical time scale for the heat to penetrate from the surface to subsurface will be actually, these time scales are much longer compared to the time scale of the irradiation of the pulse. Okay. So, therefore, again there is a strong local non-equilibrium that happens. The photons come and just hit and go, and by the time the surface responds to it, the photons are already gone and there is a big non-equilibrium there. So, there is also a chance that you have a hotspot generated. Okay. So, if you look at some of the applications at in nano electronics, and some of the applications in also metal cutting and so on, they use femtosecond lasers. Okay. So, you have a very strong local thermal non-equilibrium. So, it is not only a small length scale problem, but also a small time scale problem here, and therefore, once again you cannot use the continuum approximations. Okay. So, you also have lot of other applications where you deal with this kind of non-equilibrium, not only in lasers, but now what we call as optoelectronics, nanophotonics and so on. So, these are advancements that are made to have a newer way of creating microprocessor chips using optical based phenomena. Okay. So, So, they say that for example, the nanophotonics chip compared to using electrons. So, you are using the light as a medium, and you can achieve the processor speeds which can be 1000 times faster than the what we have as a petascale supercomputers right now. So, these are all little bit futuristic, but you should understand that the non-equilibrium problem can become more challenging in the future when you are talking about higher speeds of propagation. So, the area of MEMS in general, so has not been very old. So, if you are looking at Feynman's lecture, that there is plenty of room at the bottom. So, in 1959 he was also proposing lot of ideas about controlling and manipulating devices at small scales. So, basically he was coming forward with a lot of challenging problems and offering rewards to people who can actually build such kind of micro scale devices. Okay. So, for example, in 1983 he was talking about quantum computing. Okay. So, that was one of the beginning ideas. Later on quantum computing took off very well. In 1990s micro machining and MEMS then took off as a very active research area. If you look at many of the professors, I mean during 1990s 2000 was a very active period for MEMS. Okay. It still continues, but now we have understood the phenomena at micro scale far more than what it was done at that time. So, they were more eager to build the devices before understanding the phenomena. So, now that there was a bottleneck at that time, and again now we have gone back to the fundamentals, trying to understand them well, and again now we are building more efficient microfluidic devices. So, some of the MEMS devices mostly they were focused on medical applications, medical diagnostics, for example lab on chip devices and so on, and then also mechanical components, the micro mechanical components such as micro pumps, micro valves. Okay. So, once you build such kind of lab on chip devices, that means you take a entire laboratory and build it on a small chip of the order of microns. So, you need all the associated mechanical components to also make this device possible, such as micro valves, micro pumps. So, then one after the other all these micro mechanical devices had to be scaled down, and you cannot use the conventional principles of pumping, for example, right. You cannot use your conventional pumps, you have to use maybe peristaltic pumps, and so this kind of devices at such small scales, and again analysis of these devices had to be done in order to understand the fundamental fluid flow and so on. And then later on I think cooling became a very important problem. So, on one hand you have the MEMS devices for medical biomedical applications, on the other hand electronic cooling was becoming a challenging problem, because that was also rapidly advancing. We have reduced the sizes of these devices and we have the heat dissipation. So, then the use of micro channels and micro heat pipes. So, they have emerged as a potential applications for electronic cooling. So, these are how over a period of time from something as theoretical during Feynman's talk in 1959 to the recent times where we have had a fair amount of understanding and also we have developed applications. I am not very sure whether we have commercial micro channel devices for electronic cooling right now. We are still in the research and development stage, but in the MEMS area, yes, we have lot of medical diagnostic kits which have based on MEMS which have come up in the last few years. So, the other issue that you have to understand at micro nano scale is the fabrication, right. So, when you say fabrication of MEMS devices, so you cannot use your conventional machining tools and do this. Now, we have recently lot of mechanical based machining which are happening at micro scale, micro machining device. In our IIT we have purchased a big micro machining device, a micro milling, micro cutting and so on. So, we have very good equipment in our institute. Apart from that, micro fabrication, nano fabrication has been existing in electrical engineering for a long time. So, they do not use the mechanical based machining device. So, what do? the photolithography. So, photolithography has been there to make these microelectronic devices, semiconductor chips. Okay. So, this can also be used for creating mechanical devices. The MEMS devices typically, or the lab on chip devices, can also be done using photolithography, but now increasingly being replaced with the new age micro machining tools. We can make mechanical devices of the order of microns using mechanical cutting rather than the photolithography. Now, photolithography has several layers of process, okay. Starting from you have to start with a film over a substrate, and then you have to prepare a mask, and you have to have a photoresist, you have to put the mask on top of this, you allow the UV light, and then it the exposed areas will be etched out and so on, and finally the pattern will be formed on the particular film. So, this has several layers and the using of the photoresist, and these are little bit expensive. So, now these are good on a really small scale and making small devices, but if you want to make so many of them commercially, so especially when we talk about mechanical devices, so becomes a little bit difficult, and therefore slowly the transition has been moving towards using this micro machining devices as well. For example, this figure shows this is a dust mite, okay, and this dust mite you may know, you cannot see with your naked eye. These dust mites are really of the size of microns, and there are some gears which are manufactured by MEMS technology, and they are just compared to the scale of the dust mite here. Okay. So, these are that small. On the right hand side also you have typically some micron sized particles. So, these are of the scale of 50 microns here, and there are some associated microscale devices compared with those micron sized particles. So, a lot of fabrication efforts from the material science. So, people from primarily chemistry and material science. So, they have been working over a period of last 30-40 years to develop novel materials, synthesize novel materials, come out with the new processes for synthesizing materials at nano scale. So, for example, carbon nanotubes. Carbon nanotubes are nothing but a single layer of graphene. So, that is you take graphite and you take a monolayer of graphite. So, that is maybe of the order of a few nanometers thickness, and then you just roll it. So, just you roll it, and then that becomes your carbon nanotubes. Okay. Now, it depends on how you roll it. If you just take the graphene sheet and you just roll it normally like a straw, you get a carbon nanotube, and you roll it like a ball, you get what is called as a buckyball here, or they are also called as fullerenes, okay, for which these people who discovered this structure won the Nobel Prize in 1996. Okay. And Lijima synthesized carbon nanotubes using arc discharge method. Now, these were some of the novel materials that paved way for discovering, for example, graphene synthesis, carbon nanotube synthesis, and so on. And now we have a lot of different nanowires, nanoparticles of different materials that you can imagine. Okay. And there are different fabrication techniques using chemical vapor deposition, PECVD, plasma enhanced chemical vapor deposition, and so on. So, also if you look at the area of characterization. So, once you make these nanostructures or carbon nanotubes or nanoparticles, nanoflowers, whatever they call, so many names. So, once you prepare them, you have to characterize them, or it could be even a characterization of a particular surface, for example. So, you fabricate through micro machining certain nanostructures on a surface, and now you want to look at the height, width, patterns, and so on. So, how do you characterize this? Okay, we cannot use the conventional microscope because these are nanoscale structures, we cannot be resolved. So, therefore, we have to go to techniques which are based on electron microscopy. Electron microscopy is a is a very novel technique. So, you can either use the tunneling effect. So, the transmission electron microscope basically in this case you have the electron tunneling effect used as a principle behind characterizing a particular surface, or you can have a scanning electron microscope. So, in this case the electrons do not have to penetrate into completely through the target sample, but only on the surface level. So, these are different level. For example, the resolution of the TEM is quite high. So, it can actually resolve of the order of angstrom, whereas the SEM can only resolve surface aberrations or whatever characteristics only of the order of few nanometers. Okay, so, depending on the kind of resolution that you want, you choose whether you want to go for a scanning electron microscope or a transmission electron microscope. And again you have scanning tunneling electron microscope. So, this is also, as I said, it is based on the tunneling phenomena, which can happen when you have very small gaps. So, that so this becomes just a quantum mechanics theory, and then the electrons can actually, rather than flowing, it can just simply appear on the other end. So, this phenomena is called as tunneling. We will see that when we do quantum mechanics how tunneling can happen. So, they do not have to pass through just like a normal atom, they just emerge out of the other end just like that. Okay. So, this is called a tunneling phenomena. So, there are also other ideas. So, out of which microscopes have been made. One is called the atomic force microscope. So, here the potential or the interaction potential between atoms is used for characterization of the surface. So, here for example, there is a diamond tip here. So, we use a diamond tip because the interaction potential between the diamond tip and usually the sample surface could be a metal surface or a non-metal surface, that potential is very high. So, that this can be deflected by this potential. Okay. Whereas the spring constant of this particular cantilever over which the diamond tip is placed itself is negligible compared to the interaction potential between the diamond tip and the surface. So, due to this high interaction potential, whenever you have a surface aberration, that means there is a change in the height locally, the topology is changing. So, this potential changes, the force changes, and therefore, there is a deflection of this particular cantilever happening, and this deflection is mainly due to the topology change. Okay. So, with this you can actually also measure the surface topology. Okay. So, the atomic force microscopy is also a very useful technique, and this was actually invented in Stanford University, but the device was built by IBM later on, and I think they collectively won the Nobel Prize for this device. So, let us quickly move on to the other applications apart from the micro nano electronics what we discussed. So, you can also talk about alternate energy sources, okay, what we call renewable energy. One form of this is called thermoelectric energy conversion. Okay. You may be all aware of the principle of thermoelectricity from your physics, high school physics. So, you can use the Seebeck effect for power generation or the Peltier effect for refrigeration. Okay. In the Seebeck effect, you have a hot side, this is the heat source on one end and a heat sink. So, this is a heat engine typically. So, you have a source and you have a sink, and you are basically transferring heat from the source to sink, and in the process you are doing some work, and the work here is electrical work. So, this is the current that is generated, and how it is generated here is due to the transfer of electrons in the n type semiconductor from the source to the sink, and the transfer of holes in the p type semiconductor from the hot side to the cold side. So, collectively it means that the electrons are flowing through this in a closed loop, thereby producing a current, right. So, this is the principle of Seebeck effect. So, that means from the hot side the electrons and holes have enough kinetic energy to move towards the cold end, and in the process they flow through a closed circuit and thereby producing current. Now, the reverse effect is is utilized for refrigeration. This is called Peltier effect. So, in which you actually pass current, right, and therefore, you basically absorb heat on one side and you deposit heat on the other side. Okay. So, in the hot side, so this is the refrigeration process. For example, you want to maintain this side cold. So, therefore, you want to absorb heat from the cold side. So, you can only transfer heat from a lower to a higher temperature only if you put in work. Okay. Otherwise, you are violating the second law of thermodynamics, right. So, the work that you are putting here is current. So, this principle is used in Peltier effect. Now, what is actually causing the the thermoelectricity or the Peltier effect to arise? If you go inside and you do we will do this quantum mechanics, solid state physics and statistical thermodynamics. So, from the solid state physics, we have what is called as density of states. So, it tells you at each energy level what is the average density of electrons that can actually occupy. Okay. So, this is given by curve like this, and on top of that does not mean that all the electrons are only occupying this particular portion here. Okay. The actual occupational probability is given by the Fermi-Dirac distribution function. This is coming from the statistical thermodynamics. We will see all this, but you should understand that Fermi-Dirac distribution function is an equilibrium distribution function which governs the occupational distribution, probability of occupational distribution of electrons primarily. Okay. So, that is given by a distribution like this. Okay. So, now if you want to calculate what is the density of occupied states, it is like this. You have a house which has say 10 rooms, does not mean all the 10 rooms have to be occupied by all the people. You have to now find out how many number of people are there in the first place and what is the preference of each of this person. So, somebody wants to occupy room number 2, somebody wants to occupy room number 5. So, the number of rooms that are available to you is basically the density of states. Okay. The probability of occupying each of this is given by the Fermi-Dirac distribution function. So, once you now take a product of these two, so then you get the density of occupied states. Then you will know two people may want to occupy say room number 2. Okay. So, one room may be completely empty and so on. So, finally, you come out with a curve which is density of occupied states, and which shows that in fact most of the average energy is focused around this energy band here. Okay. And this turns out to be the average energy of the conduction electrons. This turns out to be the conduction band. Okay. So, if you therefore calculate the the average energy will come out to be somewhere here given by the solid line. So, these are the average energy of the conduction electrons, and now you have the reference energy which is called the Fermi energy, which is at a given temperature, say room temperature, you have a Fermi energy level which is somewhere here, and this difference between the average energy of conduction electrons and the Fermi energy gives rise to thermoelectricity. So, the higher the gap between these two, the more is the amount of current that you will get for a fixed temperature difference and so on. So, and similarly for the given current you will find greater temperature difference. Okay. So, therefore, this temperature difference is the driving potential, or this energy difference between the conduction electrons and the Fermi level is the driving potential for thermoelectricity. So, we will see this when we talk about solid state physics, and then we move on to statistical thermodynamics, then we will be able to understand this, how do we get it. So, now if you therefore look at the kind of materials, so which of these have the largest gap between the conduction band and the Fermi level. So, if you take the case of insulator, semiconductor and metal, in insulator you have probably the biggest gap, band gap, right. and semiconductor it is moderate, metal it is almost 0, right. So, that is why you have all the electrons just climbing from the valence to the conduction band in metals very quickly, and they are very good conductors of electricity and so on. Whereas, in insulator hardly any electron can jump from the valence to the conduction band so easily. Okay. However, what is happening here is not only this gap, but also you should also look at the average energy of the conduction electrons. So, in the case of insulators you hardly have any electrons in the conduction band. So, therefore, the average energy itself is very small, quite small, and in the other hand metal you have a very large energy of electrons in the conduction band, but the band gap between the conduction band and the Fermi level is almost 0. Okay. So, these are two extreme cases. So, therefore, we introduce a factor called power factor, which is the product of S square is called the Seebeck coefficient, S is called the Seebeck coefficient, which is nothing but an indicator of thermoelectricity. That means, the higher the difference between the conduction band and the Fermi energy indicates a higher value of Seebeck coefficient. Okay. So, we need to have a power factor which is S square times the electrical conductivity sigma. So, if the electrical conductivity is small, as in the case of insulator, although the value of S is quite large, the product of S square sigma will turn out to be considerably small, and the same with metals, although the sigma is very large. So, your S is quite small, and therefore, once again you have a very small value of power factor. So, whereas in the case of semiconductor, this is where you have the optimally high values of S square sigma. Okay. So, you have moderately large values of S, you also have a moderately large value of the electrical conductivity. So, therefore, what is the most common preferred materials for thermoelectric power generation? They are the semiconductor materials. Okay. So, most of the thermoelectric materials here use the semiconductor based materials for producing thermoelectricity. And again, now when you talk about these thermoelectric materials, we have to characterize their performance in some way. So, we know that the Seebeck coefficient is a good indicator of thermoelectricity. Nevertheless, there is a term called the figure of merit, okay. So, which is denoted by the power factor in the numerator, and in the denominator we use the thermal conductivity, okay, multiplied by the temperature to make it a non-dimensional number. Okay. The units of S square sigma by K turns out to be 1 over Kelvin. So, in order to make this a non-dimensional number, it is multiplied by the absolute temperature, and therefore, it becomes a non-dimensional figure of merit. Now, if you look at again, if you look at the cases, however, in semiconductors, the Seebeck coefficient, electrical conductivity and thermal conductivity, they are all strongly coupled to each other. So, you cannot say I take a material with a large power factor and a very small thermal conductivity. It turns out that if your power factor is very large, your thermal conductivity also turns out to be large, because for example, if you talk about electrons, so the electrical conductivity and thermal conductivity of electrons are directly proportional. Okay. So, higher the electrical conductivity, higher the thermal conductivity. You do not find a material where electrical conductivity is very high, thermal conductivity is very low. Okay. So, therefore, the higher the power factor, the higher the thermal conductivity. Now, why do we need low thermal conductivity here? Because if you look at this particular example, so you do not want the heat to conduct from the hot to the cold side very fast. You want the temperature difference to be maintained, only the electrons and holes are supposed to flow, not the heat. Okay. If the heat also flows, then the amount of thermoelectricity will naturally reduce. Okay. So, therefore, this figure of merit brings in the factor that your thermal conductivity has to be low while the power factor has to be high in order for the performance of the device to be very good. However, these are interconnected, and therefore, this becomes a problem in designing a very efficient thermoelectric device. Okay. So, now therefore, thermoelectric power generation has some applications. For example, the Voyager spacecraft had power source because they are so far away from the sun, they cannot be powered by solar panels, and therefore, the thermoelectricity was used to power these spacecrafts, and some of the Navy electrical ships also use thermoelectricity, for example. Okay. You can also talk about waste heat recovery in for example, cars. You have so much of heat and temperature difference between the waste heat and the ambient. You can use that to power at least some of the devices in a car. At least the dashboard can be illuminated from the rather than from the battery, from the thermoelectric power generation and so on. So, you have a lot of applications. Refrigerators are also available. In fact, there are some portable thermoelectric refrigerators which cool your fluid. You can put your cool drink into that and store it at maybe 5 degrees for a extended period of time, and all these are based on thermoelectric refrigeration. However, they are not used at such a large scale. So, why? Because if you now convert this thermoelectric figure of merit to a equivalent engine efficiency, just like you have your Carnot efficiency. So, you have your thermal efficiency, and therefore, the power generation efficiency, if you plot it, you will find these thermoelectric devices are all having efficiencies less than 20%. Okay. Why? Because of the low figure of merit. So, here these are all plotted for different values of figure of merit. So, the figure of merit of all these thermoelectric devices are typically very low, and therefore, if you look at compared to your thermal power plants which are having efficiencies of the order of 30 to 40%. Okay. So, these suffer from low thermal efficiencies. Okay. However, they are very clean energy sources. Okay. And if you devise if you have good efficient materials, thermoelectric materials, so that they are the bottleneck why they have low figure of merit, because the figure of merit is tied to only 3 parameters. One is Seebeck coefficient, electrical conductivity and thermal conductivity, and all these are material properties. Okay. So, if you come out with better materials, I think this can be pushed up at least to equivalent to the conventional power plants, and therefore, they can be used more widely in other applications as well. Okay. So, this is where the nanoscale materials play a role for thermoelectric, because what you see is the value of Zt plotted as in the y axis over period of time, and you see as long as you are using bulk semiconductor materials. Okay. So, you are not getting a value of Zt above 1, okay, and you see the value of Zt of 1 will give you a efficiency which is always less than 20%. Okay. So, suddenly in the year 2000 people started using what is called as thin films or super lattices. These are called super lattices. You have thin films of 2 different semiconductor materials sandwiched together, okay, and based on this they got a value of the thermoelectric figure of merit to be above 4. Now, if you see that if you have a thermoelectric figure of merit of 4 and you are operating in the lower temperature range, because the temperature ratios with thermoelectric generation is usually in the lower end, you cannot use it like you use your internal combustion engines, you do not operate at very high temperature ratios. So, at this range with the thermoelectric figure of merit of 4, you can push it to 30%, close to 30%, and if your thermoelectric figure of merit climbs to 7 or 10, you are pushing this close towards 30%, right. So, this is where the role of nanoscale materials come into picture. You can use these nanoscale thin film technology for as potential thermoelectric materials. Okay. So, I will stop here. I think I have maybe a few more slides to discuss before we stop the PowerPoint introduction and go to the board. So, we will continue this on Monday on Tuesday the next week, and we will then gradually go to the board and start deriving some basic introductory equations and so on. Okay. So, thank you very much.